Hi guys, Tutor Marvis here. In this tutorial, I'm going to be talking about circle theorem, and I'm going to be demystifying the theorems that are particular to circle geometry, and I will endeavor to simplify it in such a way that it will be easy for us to get. Alright, so let's start by talking about the parts of a circle. The parts of a circle. Since we are discussing circle theorem, let's talk about the parts of a circle. Alright, first of all, what is a circle? A circle can be said to be a round figure, like you can see, a round figure whose boundary consists of points equidistant from a fixed point. Now, that fixed point, alright, is the center of the circle. So when we say that a round figure whose boundaries consist of points equidistant from a fixed point, the word equidistance means equal distance. So it means that from this point to this boundary, 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 they must be equal for it to earn the title of a circle. Alright. And the boundaries are known as the circumference of the circle. So the borderline that forms the circle is the circumference. And the center of the circle, this center, is the fixed point from which all points on the boundary of the circle are equidistant. Then we can see that there's a straight line from this end to this end. A straight line from this end to this end, labeled as diameter. So the diameter is the line that divides the circle into two equal parts. So when the diameter divides a circle, the areas bounded by a diameter, this place and this place, is known as a semicircle. Alright, let's start taking notes. The first thing we said was a circle is a round plane figure whose boundary consists of points equidistant from a fixed point. And I already said that that fixed point is the center of the circle. So after talking about the circle, let's talk about the center of the circle. That is the fixed point from which all points on the boundary of the circle are equidistant. Okay, now, so that will lead us to talking about the diameter that I already discussed. Diameter is the line that divides the circle in two equal parts. Okay, so this straight line here is known as the diameter. So this is a semicircle, this is a semicircle. So number 4, let's talk about the semicircle. That is half of a circle, or the area bounded by the diameter of a circle. All right, then that will lead us to talking about the radius. All right, radius simply is half of the diameter or the distance from the center of a circle to any part of the circumference. Any part of the circumference. That's what we call the radius. Okay, so it means that if I draw from this center, if I draw a straight line here, this straight line is a radius. If I draw a straight line here, this is a radius. If I draw a straight line here, this is a radius. If I draw a straight line here, this is a radius. So the distance from the point, from the center of the circle to any part of the circumference is known as the radius. All right. So let's talk about the circumference. That's number 6. Circumference. Circumference is simply the boundary of the circle, or we can call it, or the borderline. The borderline that forms the circle. Okay, now, so let's look at this. This line, all right, so this borderline is the circumference of the circle. And when you cut the circumference, all right, like this, what you have is an arc. So part of the circumference is an arc. So let's talk about the arc. So the arc is simply part of the circumference. Part of the circumference. So simply from here to here is an arc. All right, just like you are seeing here, this is an arc. And if you are cutting the circumference into two like this, it means that you are going to have big arc and small arc, which we often call the major arc and the minor arc. All right, so the next thing we are going to be talking about is the chord. The chord. So looking at what we have here, we can see our chord. This is the chord here. This is the chord. So what is a chord? A chord is a line segment going from one point of the circumference to another, but does not go through the center of the circle. So this chord is going from this end to this end. So that is a chord. Let's take note. So that is number 8. Oh, sorry. Let me use blue pen. Okay. Chord. A line that goes from one point of the circumference to another without going through the middle of the circle. Because once the line goes through the middle of the circle, it is no longer a chord, it is now a diameter. All right. So if a line goes from one point to another, that is, if a line is joining 2 points on the circumference, like this, it means that we are going to have areas bounded by that line. So the areas bounded by a chord is known as segment. Areas bounded by a chord. So this is a segment, and this is also a segment. So for instance, let's have a chord, let's have a circle. Okay. Now let me draw a circle here, a smaller one, so that you can relate with what I'm about to talk about. Now I have this circle, all right, and this is the center, for instance. Now, if I have a straight line, which is my chord, this way, so what I am saying is this area here, all right, is known as segment. This other areas too is known as segment. So this place, this small segment is called minor segment, while this bigger place is called major segment. So the areas bounded by a chord is known as segment. So let's take note. A segment, that is areas bounded by a chord. Segment, area bounded by a chord. So we have major segment and we have minor segment. So the next thing we are going to talk about is sector. All right, let's talk about the sector. Now we said that when we have half of diameter, we have a radius, all right? And we also said that from the center of the circle to any point on the circumference is a radius. So this is a radius and this is a radius. So now, this section that is created by these two radii is known as a sector. As you can see in this place, from here to here is a radius, from here to here is another radius. So the area created by two radii is known as a sector. So we have major sector and we have minor sector. So sector is the section of the circle created by two radii, or the area bounded by what? Two radii. So that is a sector. All right, let's talk about tangent. This is a tangent. A tangent is a straight line that touches the circle at a single point. So a tangent touches the circle at a single point. For instance, If this is a straight line touching this circle this way, this is a tangent. If it is touching the circle this way, this is a tangent. Alright? And even if it is this way, this is a tangent. So let's take note. That's number 11. So tangent is the straight line that touches the circle at a single point only. Then we have number 12. So the one that looks like tangent, if you observe this diagram, is a secant. Alright? It's a secant. But the difference is that a secant goes through the circle at 2 points. So a secant goes inside the circle and touches this point and also this point. So that is a secant. So let's have it. Secant. Secant is a straight line that touches the circle at 2 points. So it goes through the circle. It's a straight line that goes through the circle, goes through the circle and touches it, that goes through the circle and touches it at 2 points. All right, so that is a secant, and that is the end of parts of a circle. So we can now proceed to talking about the different theorems that are related to circles. So, theorem 1. A straight line drawn from the center of a circle to bisect a chord is perpendicular to the chord. A straight line drawn from the center of a circle to bisect a chord is perpendicular to the chord. Alright. So what this theorem is simply saying, let's see this circle. It says a straight line, this straight line, this one here, this one, drawn from the center of a circle. So let's say this is center O. Alright. And this is a chord. Let's say chord PQ. And let's call this place A. So it says this straight line bisects this chord PQ. And that this straight line is perpendicular. Perpendicular simply means it's at 90 degrees. So this place is 90 degrees. This place is 90 degrees. What other implication does this theorem, poses? If you check, a straight line goes from center O to this borderline P. So we can say that OP is a radius and OQ is also a radius. Therefore, OP is equals to OQ. We call it radii. Another thing to note is, since this OA is a bisector, it means that to bisect means to divide a chord into 2 equal parts. It means that this place is equal to this place. That is, PA equals to AQ. That's the implication. of that theorem. So let's go through the theorem again. It says a straight line drawn from the center of a circle. This straight line, to bisect a chord, to bisect means to divide this chord into two equal parts, is perpendicular to the chord. So that is, it's at 90 degrees. So this is what this theorem is talking about. So the implication of the theorem is that PA is equals to AQ, because OA is a bisector. It has divided this PQ into two equal parts. And another thing to note is OP and OQ are radii. Alright, theorem 2. Equal chords of a circle are equidistant from the center. Okay, so let's say this is chord AB. This straight line is the chord, then this is chord CD. So what are they saying? Equal chords. So if AB is equals to CD, AB equals to CD, if they are of the same length, all right? So this theorem is saying that they are equidistant from the center. That is, they have equal distance from the center of the circle. So let's call this place T, center T. Let's call this place X, and let's call this place Y. So the implication is that Tx is equals to Ty. Tx equals to Ty. And of course, this is a straight line from the center to the circumference. So Tc is also equals to Ta. That is radii. So what this theorem is simply saying is that chords which are equidistant from the center of a circle are equal. They are equal. So equal chords AB equals to CD. Once these chords are equal in length, all right, they will also have the same distance from the center of a circle. That is the meaning of theorem 2. Let's move to theorem 3. All right, theorem 3. For me, this is my favorite out of the circle geometry theorems. I love this particular theorem. It states that the angle which an arc of a circle subtends at the center is twice the angle which it subtends at any point on the circumference of the circle. So the short way to put this theorem is angle at the center is twice angle at the circumference. All right, but to be on the safe side, make sure that you know that the same arc is the one subtending the angle at the center, is also the one subtending the angle at the circumference. So what's the implication of this theorem? So let's see each of these diagram. Now, in this scenario, if our center is, okay, let me say the circumference is x, it means that my center will be 2x. Because look at this chord. Let's call this chord AB. So this chord AB, this chord is subtending a particular angle at the center, and this same chord is subtending another angle at the circumference. Can you see? So the theorem says the angle which this chord subtends at the center is 2 times the one it subtends at the circumference. So if the circumference is x, it means that the center will be 2x. Now, one thing you must understand is you need to pay attention to the direction of the angle. All right? Pay attention to the direction of the angle. The angle at the circumference, this one, this reflex here, all right, is not twice that at the circumference. This reflex is not twice the angle at the circumference. So this is the angle that is twice the angle at the circumference. All right. So if you are given reflex and you don't know this place, you need to first find this place by adding this unknown with this reflex equals to 360 degrees. That's angle at a point. So let's look at this case. If this reflex, for instance, is M and this is N, okay? So look at the direction of the angle. Can you see? Facing the same side. So we can say that angle at the center, which is M, is twice angle at the circumference. But in this case, you will notice that X is facing down, this angle, and 2x is also facing down, this angle. So that is why this angle is twice this. And in this case, you see where M is facing up and N is also facing up. Now, which arc is subtending this angle? This very arc. This one is the one subtending this angle at the center, and the same arc is subtending another angle at the circumference. So angle at the center is twice that at the circumference. So M equals to 2N. So let's check another scenario. If this is center O, and this is angle P, and this is angle Q. All right. So let's call this place P. Let's call it AB, arc AB. Now this arc AB, this arc is subtending angle P at the center, and this same arc is subtending angle Q at the circumference. So we can conclude that P equals to 2Q. So whatever the value of Q is, you multiply it by 2 to get the value of P. So this is all about theorem 3. Let's go to theorem 4. All right, theorem 4 says angle in a semicircle is right angle. What is the implication of that theorem? Okay, so look at this. You can label this A, B, C. So everything AC, this line AC is a diameter, all right? So everything to the left is in semicircle, and everything to the right is also in semicircle. So what the theorem is saying is angle B here is 90 degrees, angle in a semicircle. If we drew it this way, all right, the angle will still be what? 90 degrees. The angle here will still be 90 degrees. So no matter how you draw it or how you rotate this diagram, it will still be what? 90 degrees. So that is angle in a semicircle. All right. So look at these two. This is angle in a semicircle. So this place is equal to 90 degrees. That is all about theorem 4. So let's talk about theorem 5. Theorem 5 states that angles in the same segment are equal. Angles in the same segment are equal. So let's call this place PQ, all right? This is called PQ. And I told you that once you have a chord, the areas bounded by that chord is a segment. So let's say this chord subtends angle X here, subtends angle Y here, subtends angle Z here. So X, Y, and Z are in the same segment. Therefore, X equals to Y equals to Z. So this is what theorem 5 is talking about. Angle in the same segment are equal. The same thing is true for this diagram. So let's say I have A here and I have B here. A is equals to B because they are in the same segment. Then let's say I have P here and I have Q here. This is a chord. So P and Q are the same angle in the same segment. Therefore, P is equal to Q. So that is that about theorem 5. Theorem 6. Angles in opposite segment of a cyclic quadrilateral are supplementary. Supplementary simply means 180 degrees. So angles in opposite segment of a cyclic quadrilateral are supplementary. It simply means that when you add angles, let's say this is angle M and this is angle N, this is P and this is Q. What this theorem is saying is that M plus N must give us 180 degree, then P plus Q must be equal to 180 degrees. Then this is A, this is B, this is C, this is D. The theorem is saying A plus C is equals to 180 degrees, then B plus D equals to 180 degrees. So the sum of the opposite angles of a cyclic quadrilateral must be equal to 180 degrees. That is that about theorem 6. Let's talk about theorem 7. Alright. Theorem 7 says the exterior angle of a cyclic quadrilateral is equal to the opposite interior angle. What are we simply saying? Now, this angle here is the exterior. Let's call it A. Alright. And this angle here is the interior. Let's call it B. So this theorem is saying A equals B. Or if this angle is P and this angle here is Q, the theorem is simply saying P equals Q. So that is all about theorems. According to theorem 8, the tangent to a circle at any point is perpendicular to the radius drawn to its point of contact. Okay, so what is theorem 8 saying? Once you have a tangent, that is a straight line this way, and you have a circle, and you have a radius of a circle joining that tangent, the point of contact is always 90 degrees. 90 degrees. Then look at this one too. This is a tangent, a straight line, and this is a radius. Then this point of contact is 90 degrees or perpendicular. So that is what theorem 8 is simply saying. The point of contact of radius and a tangent is perpendicular. Let's talk about theorem 9. Two tangents drawn from an external point to a circle are equal in length and subtend equal angles at the center. So there are a lot of stuff that we need to know from this theorem. Let's label this A, label this B, this is center O, alright, and let's say the external point is T. So the theorem says two tangents drawn, so AT is a tangent drawn from an external point to a circle are equal in length. So the first thing we got from this theorem is AT equals to TB. Alright? Or we can say AT equals BT. So these tangents are equal in length. So two tangents drawn from an external point, this is the external point T, to a circle are equal in length and subtend equal angles at the center. Okay, so it means that if this AOA is X and BOT AOT is x and BOT is y. It shows that x equals to y because the subtends equal angles at the center. Another thing is this is equal to this. Now another thing you must notice is that OA is equals to OB, radii. From here to here is a radius, from here to here is another radius. So they are equal. And since OB is a radius, joining BT shows that this place is 90 degrees and this place is also 90 degrees. So these are the things that you need to know about theorem 9. Then theorem 10, the last but not least. The angle between the tangent to a circle and a chord through the point of contact is equal to the angle in the alternate segment. So this is what we always call the alternate segment theorem. Let's call this place P, Q, R, and this place is T. Okay, so we know that this straight line, I can call this place S. ST is a tangent, all right? And R is the point of contact of chord RQ to tangent ST. So this is the point of contact. And let's say there is an angle here, angle X, for instance. So what this theorem is simply saying is that this angle X is also equals to this angle RPQ. So we can also call this place X. So this place is equals to this place. The same way, this angle here, let's call it Y, is equals to this angle here, Y. So it is called alternate segment theorem. How will you recognize it in a question? When you see a chord this way, all right, meeting a tangent this way, and the angle that the chord makes with the tangent will always be equal to the angle that this chord subtends at the circumference. Can you see? So that is that about theorem. So this is what I have for you on the circle theorem, and please stay tuned as I will be dropping a tutorial on how to solve different problems using these theorems. Please do not forget to subscribe to this channel, share with your friends, like, drop your comments. I would love to read from you. Thank you.